the difference between augmented reality, virtual reality, and mixed reality. It is a range of experiences. On one hand, we have virtual reality, which is a total immersive experience where you put on a headset and you are disconnected from your environment. Everything you see and interact is a 3D generated object. And on the other hand, for augmented reality, you have a connection to your environment, like in HoloLens, and you have some extra information, maybe 3D or maybe audio information that's available to you, which is augmenting your reality. Also, we have mobile phone applications like Pokemon Go. You are looking through the glass of your phone and you're able to find 3D objects in the real world. And this whole range of experiences we call mixed reality. And short, it's called XR.
Hi, it's my great pleasure today to introduce you all to Andreas Urban. Andreas is a CEO of a consulting company. He's also a Microsoft MVP as well as a Microsoft regional director. He's a Scrum trainer, an entrepreneur, and all-around good guy. This is a special honor because Andreas and I have been friends and colleagues for going on a decade now, mostly around cutting-edge Microsoft technologies such as the HoloLens and the Kinect. Without further ado, Andreas, can you speak to us about cognitive services in VR and AR?
It's a pleasure, James, and thank you for the great introduction. Let me add a little bit more. The CEO thing, I'm the CEO of the US operations of a company called DayNet, and DayNet usually got acquired by a lot larger company called ACP from Austria. So I call myself here the CTO of Metaverse and Megalomaniac, and maybe in the talk it will get a little bit more clear why I do that. So I see the term Metaverse with a little bit of skepticism, but that's a different story. So I have over 25 years of experience, already dabbled with AVR in the 90s, but at that time things were, there was no money in it, to be honest. So I was going the enterprise route, built integration types of application for many years. And in around, well, it has been now 8-9 years ago that I started dabbling again with fun things, meaning Kinect for Windows and Kinect for Azure, mixed reality, HoloLens, applied AI, Internet of Things, and so on. And lately also Metaverse. So what are we talking about? Some things you can do with a spatial computing device, yeah. There will be maybe a little bit of demos, but in short form of video, it's just too difficult to live stream mixed reality in a short talk like this. Too many things can go wrong. Then a few things you can do with computer vision in the cloud if you're not a deep learning expert. Then we try to put it together in an example to recognize objects in 3D space to hopefully make the story round at the end. But first, let's level set briefly. So where do we come from? All this, what you see here, is not that far ago. So this is maybe around 100 years ago here. And then what you see here, those ladies, they're actually programming, well, a computer, like replugging those wires, patching. In this case, it wasn't a telephone, but was actually functionality to program a computer to do different things. It was a major input breakthrough to program a computer with punch cards. So when that got developed, and then you see here which was another breakthrough that accelerated our interaction with computers a lot, was the integrated terminal of a keyboard and a screen. Now what you see here is like basically the first mouse that was invented in 1963. So this is like 58 years ago now. Yeah, 58 years ago, the mouse is 58 years old, and this here is in 1968. You saw the first integrated conceptual device that has a mouse, a keyboard, a monitor, and a concept of Windows, which represents how most of us still working on a day-to-day basis. So this is 53 years old, basically. Now, also touch screens were invented in 1965, and the first cell phone type phone that could install apps was from 1992, 1994. What has changed in the way of we interact with computers for most of us is not that different. So maybe the screens got smaller and prettier, we have shinier pixels, or they got bigger and allow interaction maybe with multiple people. But in the end, we're interacting with a flat screen with touch or mouse or keyboard input. So like I will go over the next slide relatively briefly. So we distinguish between physical reality, that is where you are right now. You're maybe sitting in front of the computer or on a sofa, watching it on a TV, and maybe have a beverage or maybe eat some cake. I don't know. So that's your physical reality, and you interact with it. The virtual reality would be replacing that reality with something else. It could be headset, could be also something where anything where you replace your real reality. As the introduction to this video said, the blending of the virtual reality and the physical reality we call mixed reality. The spectrum is now where does the human come into play? So when humans and computer interact, we call it human-computer interaction. This term has been established for many, many years. So, and when we interact with our environment, that's our conventional reality. Now, how do we call it when a computer interacts with the environment? It has sensors, maybe, and can understand some of the environment. That would be called perception. And bundling all this are the capabilities we need to do mixed reality. So, and that's where one of the emphasis of this talk is to look a little bit in what can those devices then do in that realm of perception to besides of displaying nice pixels. Again, the spectrum from physical reality, like adding a little bit of virtual objects, would be augmented reality. Digital reality would be the complete replacement of your real reality, and we would call this experience virtual reality. All this again is mixed reality, and now this is briefly the building blocks that typical spatial computing devices or mixed reality devices have. So we have gaze, where what you look at, be it with eye tracking or just a positional direction, what your device is looking at. We have gesture, which could be sophisticated hand gestures that you need to learn, or just trying to understand how your natural hand gestures are, like grabbing something. Voice commands, be it from specific voice commands to trying to make sense of text that you speak, like in a natural way. We have spatial mapping, which is a capability to basically scan your 3D space, be it with a depth-based is a depth camera like Azure Connect, which is basically built into HoloLens 2, or you could also try to generate it from multiple observations from RGB cameras. Photogrammetry would be the term for that. Then we have spatial sound. Spatial sound is more for the output side of things. It helps you to locate objects appropriately in space, and as a developer, typically you do not need to do much. The frameworks that you use are able to position an object that you give a coordinate in 3D space if you assign a sound to it in a way that you hear it, the sound, as if it would come from that object from the proper position. If you are interested to learn more, you have, I think the abbreviations are HRTF codecs, so that would be something on that. And then the latest is the world coordinates, which is a representation of a coordinate system that you typically can store, reload, and relocate in your real environment. That's also the area where now it gets interesting when we talk about the so-called metaverse term, when you then may blend several types of virtual or augmented or XR environments with your real reality in a persistent way. Anyways, but we cannot get too deep into this topic, otherwise we would be here tomorrow. A brief and old scenario that was introduced by Microsoft and the home store type of company called Lowe's. In Germany, it would be Hornbach. In other countries, there are different stores. Basically, you can one of the things you can do there, you can buy kitchens. They developed a kitchen configurator, and you could do that with your partner, with your spouse or friend, and you would see the same thing as your partner, and you could change the doorknobs, you could extend things, and it would be all rendered nicely. But what they also got, because you have gaze and position and it can analyze speech, it was able to generate a heat map. What have people looked at and for how long? And by trying to understand the text that people said, they were able to detect sentiment associated to those heat map items. Now, okay, this sounds very intrusive, to be honest, for people who care about privacy and so on, and I cannot tell you if they really use it in production. But this is just to give you an understanding that you can do with those types of spatially aware applications, things you were not able to do before. Now, imagine you want to go home, you're done with buying that kitchen, you configured everything, let's order the stupid kitchen and go home. Now, the sales associate then suddenly would be able to say, hey, wait a moment, that's great, you want to buy it? But I believe your spouse, maybe she didn't like those cabinet knobs because she was referring to them as like, don't like, metallic, hard style, and small. So maybe change that one thing and you would be happier, and a happy customer is what I'm aiming for. So this you wouldn't have been able to do easily with a traditional sales process without a tool like that. Okay. Typical questions to solve if you work in a 3D environment are associated to those concepts here. So one would be in the, I call it location anchors the movement. For moving, you could generate a heat map where somebody is or what they're looking at for how long. You could follow breadcrumbs, a trail of breadcrumbs that people leave behind or avatars leave behind. You could set anchors and share anchors to be able to relocate things in 3D. And you could then work on the so-called mesh, the mesh being the 3D representation of that space that you're in. Now, that could be optimizing the mesh, like making a plane, that could, out of uneven structures that sensors picked up. It could be finding things on that mesh or in that 3D environment, for example, finding a wall, finding the floor, or in general, finding free space. Yeah, that's just a different rendering of that slide. Now, one of the tricks you can do when you work on 3D spaces, because 3D space is continuous and typically your coordinates are not discrete positions, but are like floating point variables, right? To reason, so you could reason on your location, on the velocity, how fast do you run around or move around, on the acceleration. You could actually even think about analyzing ergonomics by the movements that people do while they're wearing a virtual reality headset or an augmented reality headset or HoloLens. Sports games use similar tricks also to try to analyze your energy that you burned when you play that game. And one thing, however, that you could do to solve that issue that the space is continuous is if you're, for example, interested in counting people in a specific space, you could subdivide your space into a grid. A terminology for that is often voxels, and it basically means you're rounding your position to snap to specific blocks and cut off the coordinate parts that you don't care for. So you would be able to say in this block up here, in the last 5 minutes, there were 3 people moving around. Okay, that's one of the tricks you can do. And there are other tricks you can use to store information more effectively. The follow the breadcrumbs example, it will get more clear in a video. It's just to give you an idea. If you're a software developer, what does it really mean when I talk about that? So it will show some very, very basic code, but I'm not trying to explain the code to you in detail. The concept is like in the fairy tale Hansel and Gretel, you drop like a virtual breadcrumb, basically a marker in 3D space in specific intervals in time. And then somebody following that breadcrumb typically would do so with a delay in time and move to the next breadcrumb when away a specific distance. Think of that private investigator who does not want to be caught and does not want to be seen. The reason for that is you could have an avatar, like an animated character following you without running into you, as an example. As an example, I will not go into the deeps of this. Like this would be like an initialization of such a system. You have like a list of the so-called trail objects here. Those would be the breadcrumbs, and you try to remember the last place trail and so on. You care often about the floor. So you would want to find the floor of the environment you're in, and then you start queuing those things, right? Now, this would be example, how do you drop those objects? When do you drop a new breadcrumb? Basically, you look at the position and look at the distance from the last position where you dropped the breadcrumb. If you're far away from it, you would drop a new breadcrumb, right? Similar, when you follow it, you follow a breadcrumb by rotating in the direction where the next breadcrumb would be. Then you decide to walk towards that breadcrumb when your distance is larger than the distance threshold, so you don't get caught again. And then you move in that direction with a specific speed. So that's all there is behind, right? It's pretty straightforward. There will be a short video later where I have an avatar following a trail of breadcrumbs. Oh, it's actually here. So let me mute that here. The video is not very complicated. It's so I will move around in a second here. And okay, I'm moving, and now this kangaroo will at one point start hopping. Oh, actually, it hopped here. It hopped because I moved away enough, and it stops so it doesn't run into me. The other thing that's interesting in this video is the part of it. What we developed here is actually a system where we place Easter eggs, right? So that sounds okay. Why do we want to do that? Well, it's just for fun. But what is interesting about this is how we did it. So because we knew where we were, like because this HoloLens device we're wearing is able to store the history of the location we have been at, we're able to hide Easter eggs precisely where we have not been before. And when we're trying to find them, over time, we start exploring the space, and every time we find a new Easter egg, we explored a new part of the space, and we can store information about the space. So that's a gamified way that helps you to explore a 3D space, and you can use other tricks like analyzing from each Easter egg in each direction, shoot virtual arrows into walls that it may have seen to try to hide them better, to hide them in more difficult places, but still in places that can be discovered, right? So it's just the motivation behind why you do some of those things. Now let's see if I'm smart enough to continue my presentation. Okay. Now the other aspect is, what about spatial anchors? Yeah, I mentioned that before. What a spatial anchor is a point in space described by visual surroundings. So that means it needs to have distinguishable visual features in that environment. That could be an object itself that you care for, could be distinguishable enough, or it could just be the geometry around it. That could be markings on the wall, that could be corners of physical objects are distinguishable enough for a computer vision system to determine feature points behind that, and those feature points are mapped into a 3D coordinate system. That's typically an algorithm that you do as a developer, as a user, don't have access to. On HoloLens, all this magic is done by the hardware acceleration that's built in, and you do not need to do much to use it. You just say, here, save a spatial anchor, load a spatial anchor, find a spatial anchor. Now, there's a caveat that I need to mention. So I don't know, if you look now at the camera, it's probably not very large, but imagine this is me, and then there's my hand would be another person. If I look in a specific direction and move my head around on the left side of something, and then would save a spatial anchor, and somebody else would do the same thing on the right side and look at an area of space, we have seen this area of space from different angles and may not see the same visual features and have never seen this environment from the position of the other person, right? So if we have not done that, then each of us thinks they have a good spatial anchor, but the other person trying to use that spatial anchor, loading it, may only be able to find that spatial anchor when they get into a similar physical position, so that those feature points all appear. Meaning, as a practical consideration, if you are setting spatial anchors, make sure that you have explored the space enough in where you put a spatial anchor, so that another user would not be surprised by not finding it. So the other user be in that space where the users would be, simplified, right? There are other ways to use anchors, a little bit shortcuts, like if you don't want to scan a whole area, or if the area doesn't have a lot of clear distinguishable features, you could make some specific markers to lock things in. If you put a 2D barcode, a QR code, where you know the size, then you can also use that to scan and agree on a spatial coordinate system based on the position of that physical marker, that QR code, or something like some vendors have, like a Fourier tag and so on. Again, setting an anchor on mixed reality on Windows only needs nothing but a name. You can anchor a hologram, and there's no repositioning of that hologram afterwards possible. You can have multiple anchors per screen, and each application has its own anchors. Another motivation to set anchors is, from a visual perspective here, that it helps the system to give you good visuals. Now, imagine I'm here, I'm setting an anchor right in a 0 position, and then I move 5 meters away, and then I look at something, an object that was where initially was, right? Now the cameras of a device like HoloLens try to make sense of all that and try to find those feature points. The problem is those feature points are now really far away, and the imaging sensors of HoloLens will see them really, really small, and the pixels of the imaging devices will get less and less precise the further away we are. I mean, the differences between that. And so think of it like a lever effect. We have a small measuring mistake, and if we're close to it, it's not so bad. But if we're really, really far, then suddenly like a difference of 1 degree would suddenly be a difference of a meter in real life, right? That's why you would also set multiple physical spatial anchors. Now, what's the thing with a spatial mesh? A spatial mesh, think of it as a bunch of triangles describing the geometry, and it approximates what the HoloLens depth camera has seen, right? So meshes can be messy, so often you want to clean up those meshes for them to be actually usable, because they just derive computer vision from real-time observations. That probably gets more real when I show you a video in a bit. One of the examples that you often have to solve is how to make a plane out of your space. It could be very simple. Straightforward would be to just mark 3 positions in space, 1, 2, 3, and draw a plane between them. Or you could select a lot more points and average out mathematically what would be a good plane that approximates all of them. Or you could walk around this mesh from a central point and try to find a plane. And there are many other approaches that are how you can solve that. Now, what is this thing with spatial understanding or scene understanding? This would be now reasoning about what can be derived from a spatial mesh. So typically you need to pre-process the mesh, and examples could be identifying a wall, identifying the ceiling or furniture, finding free space on the floor or on the wall or another surface, and then maybe add virtual objects to proper locations. Now, how's it done, right? It's basically math and logic on the spatial mesh. There's some accelerated processing available in some scenarios that can be baked into silicon, or you could use pre-trained AI to recognize some specific scenarios. The latest approach on HoloLens 2 is scene understanding. We have two technologies available. One is spatial understanding that has been around since HoloLens 1 in the Microsoft ecosystem, and the other one is scene understanding. Spatial understanding, you can find it in the Holo Toolkit branch of the mixed reality toolkit still. You can still use it, but it's a little bit involved. And scene understanding is the latest one that's a little bit faster, but a little less flexible. To give you an example, this is for spatial understanding. What were queries like? So we're looking for something with a specific surface height, with a specific numbers of surfaces. Is it a rectangle? And is it not part of the shape couch? Then it may be a chair, right? So basically, it's a bunch of rules that behind of each of those rules is quite a lot of math where you analyze the spatial mesh. This is just to find suitable areas. It's just, I'm not going to read this code to you. I'm just going to skip over it. The point is that you do a lot of math on it and set some rules where you count, where you try to find things in a specific height of a specific size that you can, for example, sit on. Scene understanding is the new approach from HoloLens 2. I thought I put a link in here, but I must have somehow used the wrong background color and so on. Please look it up in a search engine, scene understanding. There's a dedicated SDK for it, and I will show you a video in a second of both of those, right? There are other more naive approaches that can also be very successful. You can use a game engine collider sometimes to make sense of your scene. When you have a mesh, you can bind it with a physics engine and then, for example, do a so-called box cast to it. So you throw a virtual object in it and the colliders will tell you if it hits something, and then you turn on your physics and the object drops down and maybe finds a comfortable position for it to be in. You can use that actually to position things also. Now let's try to look at some examples of what that looks like. Where is it? So, okay, audio off. This would be an example how you do spatial understanding. First of all, you would need to scan the whole room. Yeah, I'm going to skip over that. You see in this, the engine and the C++ code that is available as source code you can use in Unity apps. And what's unique here is that it cleans up the mesh. You see that those meshes are very regular once it's scanned it, and it will try to close holes into that mesh. It takes a while to scan that, so let's skip ahead. And around, I think, minute 7, I'm happy with it. And now I scan the whole environment, right? And then you can do those queries, the example queries available. You can explore and understand how they're done and extend them. Let's say, what are we doing here? First, yeah, let's find suitable areas. Click, and you see that it will position possible suitable areas around the space, which align in height what a typical chair would be like. Yeah. Again, all this you can use just example codes that is around for free for you. You don't need to develop this yourself. And another example would be positioning things on edges. That's actually very interesting here. On surface edge, click, and now it is positioning objects not just on a surface, but actually on a corner of that surface. That's actually pretty nice, right? And finally, let's try to find a final example. Would be to find the, where is it? Okay. This is here where I found the biggest wall. So if you want to use a virtual movie theater or find the biggest wall to put content on, you can run such a query and you get a 3D. You get the bounding box of the wall you can interact with. That would be the spatial understanding part. Now let's look at the scene understanding briefly. That's in my parents' house here. And so when you load it, it starts scanning it, and it will immediately try to make sense of that environment, and it has a few baked in concepts, like being the floor, which is green. Then it marks some things as backgrounds, which is just, okay, it knows it's a surface, but it doesn't entirely sure if it's feasible to interact with. And then there's, for example, here is a platform that's our the kitchen table or breakfast table of my parents. And there are a few other markers for the ceiling and for unrecognized objects and so on, right? The visualization, don't worry about it. You can switch it. That's nothing you need to use. It's just a way how to conceptualize it here for you visually. You can also look at it from in a dollhouse perspective. So it renders as a dollhouse, and so my whole environment would be scanned as a dollhouse, and you could look around it and in it. So let's see. So it's just, okay, that's enough for this example. Here's an example of object placement. When you have this environment, you could then give it like a command, like place objects there, and combining a physics engine in this now optimized mesh without holes, you can relatively easily place objects in that environment that feel as if they interact real with that environment. Okay. Then it supports the query to mark a floor area. So in this example, we say like find me floor, and it recognizes this area as a floor that has enough space around it, so you could do something and position something there without hitting other objects around it. This is not a big house, so there are not a lot of large floor areas around. And finally, here you can analyze the space as a so-called nav mesh, a navigation mesh, meaning Unity, for example, has a concept of a navigation mesh which defines areas that virtual objects can move around, or game characters can move around without bouncing into objects, without getting stuck. For example, in this case here, I tried to tell that chess piece to move somewhere where there's a couch behind, and it was stopping at the couch because it cannot, our sofa, it cannot move any further. Okay, so let's try to continue here. Like a quick overview of cognitive services and applied artificial intelligence. So Microsoft, or in general, most cloud APIs are now these days done in with RESTful interfaces, and you can expect an API wrapper for most languages. You have a pattern, you set up resources in the cloud, you get access through credentials and tokens, you use it in your applications, and you pay per use. In the Microsoft case, there's often a free tier available. And on the Microsoft side, we have two types of those smart services currently. Those are cognitive services. Those are API-driven services that are multi-purpose, and they're easy to integrate. And there's applied AI. The differentiation is relatively recent. They found that some of the services are a little bit more specific. For example, Azure Form Recognizer to easier scan invoices or other types of custom forms, or Azure Bot Service to develop bot interactions. This is a list of currently available cognitive services in Azure, or the type of services rather. We have decision type services, language type services, and speech type services. There's some crossover in some case between translation, between text and actual speech. And in our case, we have a few vision-based services on the right side that we will talk about briefly. This is computer vision, custom vision, and face API. On the applied AI services side, there are two mostly vision-based services, which is Azure Form Recognizer and Azure Video Analyzer. We will cover briefly Azure Video Analyzer. So those are the vision-based services in that ecosystem. Now you could ask, why is Microsoft doing that? Well, they want to make money, and they have Microsoft Research, who is cutting edge and invents things that are often may take a long time to productize them in a way that you could install it at home, and the intellectual property would be protected. So they decided, it was one of the initial motivations, to make them available in the cloud, to give those smarts of their researchers, make them accessible to anybody. So computer vision, and we will have demos for each of those. But in order to do a lot of swapping, I will run over the description first. Is basically computer vision capabilities bundled in one API, like extracting text from images, image understanding, such as detecting objects, assigning tags to a scene, detecting faces, and get some metadata about that scene, and in general get information. There's a preview service called Spatial Analysis, which is a little bit more involved, that does things like is more optimized for video streams when you want to make sense of a space. That could be analyzing parking spots in a parking garage, or in this case, analyzing the distance between shoppers as they move, get some relevant information in COVID times. Are they wearing a face mask? How fast are they moving? Do they congregate in an area, and so on. This can run also on the edge, meaning not in the cloud, in a container, so they still have the things somewhat protected, but it's accessible to you as a container only and not as a model, right? Face API, we only covered very, very briefly. It can be used to identify people. Up to 75 million identities are supported, so you can almost have the population of Germany face recognized. Microsoft is conscientious about abuse of this service, so they will currently not work with law enforcement companies, organizations in the United States and other countries, to my understanding. And but you can also have, but some, so who uses it? It's mostly used by companies that have often loyalty programs, where you are a fitness club member and you walk into the fitness club and they should recognize you immediately, right? You can find similar faces and group faces and get all sides of meta information out of that. Now, custom vision is a service where you can do image classification and object detection based on things that you as a user provides. And it does not need large data sets. Behind the scenes, it uses transfer learning. That's the trick of it all. So with 15 images of one type, you can already train a model to make sense of something, right? So let's briefly look at computer vision and face API in custom vision. I will show most of those demos only right now on what's available on the website, but all this is available in code also. So this is an example of output that you would get with the scene, where you have a subway station and a train rushing in, and a few people. You get a list of objects, and this is basically JSON with confidence intervals and bounding boxes. And you get also object hierarchies for some type of objects. For example, here, a subway train is also a train, which is also a land vehicle, and which is also a vehicle. And you assign confidence values based on what it is. And of course, the confidence gets larger, the less specialized you are. Then it assigns tags to the whole scene, and even a description to what you're seeing at people waiting at a train station. Meta information is available, and so on and so on. Now, you may guess already that this is not just one convolutional network behind the scenes. This is a lot of API calls that get triggered by an API call. Meaning, as a user, if you tell computer vision, give me everything, it gives you everything, but you also pay more money, right? So just to be clear about that. For OCR capabilities, here is an example for OCR, where actually I have the OCR example only in real code, but here for this, but here that's the one that you can follow. Here would be this scanned label here, and it gives you bounding boxes and text that is associated with those different bounding boxes, right? So it doesn't give you completely free text. You still need to make sense of it and analyze those bounding boxes and try to find out what's relevant to you. Why does it matter? Because in this case, for example, if you would go back to this, you may get text fragments that may not make sense, and you only depending on the position of that text fragment, you may want to include it in your results. Custom vision. Here are a few examples. In custom vision, that if you have a web portal, but everything is also available via APIs. The web portal does nothing else as calling those APIs. You could run a new project and let's say dummy, give it a description and a resource. The resource is then what you pay for in Azure, and you say one classification object or object detection. The difference is in classification, you have labels assigned to the whole image or multiple labels. For example, multiple tags per image would be you take an image of a brown cat, and yes, you would mark it as a cat, but you could also mark it as a brown animal. And then you take an image of a brown dog, so it may also have the label brown animal, but it obviously does not have the cat label. Right? In object detection, you will mark specific parts of the image that you care for. I will show you in a second what that is. And then you have different domains. Yeah, the domains are optimizations for specific scenarios. General A1 and A2, you would need to read the documentations are optimized for some cases where things are more similar or not so more similar. The newer models, newer systems are a little bit faster in general, but there are some cases where the first one is a little bit better. Food, landmarks, and retails are each optimized for different scenarios depending on what you see. Like, for example, food has different color palettes typically in typical shapes that you may see, be it banana, broccoli, be it food packaging. Is very different from retail packaging for toys and so on. And landmarks, again, would have completely different characteristics. They use that to do some proprietary pre and post processing, and also to use a different pre-trained model that they then apply reinforcement learning on, where they only replace the upper few layers. The compact models, the difference there is that you can export those. You can export those to run on your local device. Could be a phone, could be a HoloLens in different formats. For example, Onyx is one of them, and we will actually have a demo at the end that uses such a model. So to briefly show, this is to conceptualize what it is. This is a very simple demo I did. I started wearing glasses recently, so I trained the model to recognize me in my specific environment in my home office, with glasses and without glasses, and I can do a quick test and give it a file that has not been trained with, and I upload that, and hopefully will say that I believe I'm wearing glasses. Word of caution, this only works well in this specific environment. As with all AI training, your training scenario, training images should reflect what you also later expect on. So if I would do that outside somewhere, or compare me with glasses versus without glasses outside versus in this specific environment, I would get different results, because behind the scenes it also learns, that there's a bright spot here and that there's a shape like that here, and will use that knowledge. We'll get back to custom vision in a bit. It is a part of another demo. So the last part is video analyzer that I wanted to briefly mention. It combines a lot of different services together, right? Transcoding, audio effects, transcription, and to show it in action, what it means is basically can be used to analyze a real video and to get insights into that video. Now it's loading. And so in this video, for example, it extracted it extracted keywords. It found, for example, if I want to find a car in that video, so it will give me
about power of the fact.
It will give me locations in the video where the car has been. So it also can recognize brands. For example, the Microsoft brand, it's recognized here, but we found that it doesn't recognize the Microsoft brand often enough and good enough because it only uses text. So what we did in our case, we used a computer vision model and a custom vision model, and specifically trained it to be better in recognizing the Microsoft logo. And that is an object detection model, right? So you see here all the little bounding boxes. Then I export that and run it against the, where is it? I think that's it. And I run it against that, the images. So this is, I will read that run in the background. This will try to make sense. That will try to find better representations of the Microsoft logo that the video analyzer would not have been able to detect, and that custom vision in some cases may be able to detect based on the color of based on the logo, or computer vision may be able to detect because of the baked-in logo recognition that it has. Yeah. So you see here it recognized it in 2 spots. A call like this in a C# API gives you various predictions with a probability, so you can make sense of where the Microsoft logo would appear. That would be custom vision. And another call would be computer vision that will give you the same, in a slightly different format, where the Microsoft logo appears. So you can get more meaningful results in some cases. Now let's go to the grand finale soon. So if you want to combine everything, right? So what could we do, right? There's an interesting scenario with HoloLens. So HoloLens has a camera, right? And the camera has, they call it frustum, that defines the view cone, basically the trapezoid where it sees things, and it has a coordinate system. Here's the origin of the coordinate system, and here are the points it sees. Now, you as a user, each of your eyes, each of the screens has its own coordinate system. Now, the trick is if you want to, for example, see something here based on the camera, you would need to transform the coordinate system. The concept behind that is called locatable camera. Now, what did we do? So we recorded a video early in the session room and then used computer vision to get insights into each frame of the video and analyzed results to get most frequently recognized objects, uploaded that to custom vision, trained a model automatically, and then that model will run on HoloLens. To briefly show you what I'm talking about here, this is something we did at another conference. So here we would just analyze all those things. So here's a chair, then here's a person, and so on. So it will grab all those frames and then count what have I seen often enough. And if I have seen things often enough, then I will upload it to the cloud and to build a custom vision model. So in this case, a model like this. This model has a lot of chairs, for example. Here's some chairs. And so it will, so this model now is very specialized, but automatically generated and is able to recognize chairs and maybe people in this very specific environment. Yeah. So it doesn't recognize chairs that look different. It may not recognize people in a different environment. To show you what I mean here, and I have another example like this. So here, remember when I talked about the viewing angle and so on? So what we did here, this is basically the location of the camera as it took a picture. And then those little ugly rays here are marking things at seating. And basically, we're storing and learning about space, where things are in 3D space, based on our position where we have been, the known camera characteristics, and the ability to persist location. So this is very prototypey and could be made better. But imagine you could automatically, like with a lot larger model, like over time, annotate your three-dimensional space and combine that with the other things we have seen before to make sure that you actually position your observations where there's a real wall or a real floor, to not to make sure they exist in somewhere in Nirvana. And use, for example, the voxel system that I introduced also earlier to then annotate your, let's say, it's like 1 by 1 meter areas of your office building by, okay, I've seen seating here and I've seen a computer here on the podium and so on. So I have been a little bit slower than I expected, but I'm through with my slides at this point. And I hope that you got some helpful information from it. Yes, that's a similar video. You can get it later on of my own house. The summary is of spatial computing, what you can do with it, how you can use computer vision in Azure, and being smart about understanding your 3D space. Thank you. If there are any questions, I'm happy to hang out later.
Thank you, Andreas. That's fantastic. Thank you for going so much in depth into both the cognitive services and also the HoloLens to the point of getting into the code. I think most speakers tend to be a little bit shy about doing that. So it was fantastic to see you do that. I think we've got time for just a couple of questions, if that's all right with you.
It's all right with me, and also my information is here. People can reach out to me afterwards also.
Okay. So we've got a question from Kasim. Kasim wants to know, could you go into more detail about use cases for combining AI with the HoloLens?
Mm-hmm. Well, one of the things I try to, one of the examples I tried to give was to help to navigate a 3D space would be by learning about what's in that 3D space, right? So where do you find things that you're looking for, and without needing to consciously inventory it to learn about that. Another example could be assistive technologies for people who are blind, for example, right? So HoloLens is good at locating itself, its own position into a known space, and basically think of it like a GPS inside. When you combine that with things like Face API, which I've shown before, Face API, which I mentioned, I haven't been able to show it, gives you information about people you see. For example, how approximation or how old they are they smiling, are they not smiling? So it can give you some ideas in that sense also to help people who have vision impairment, for example. So you could then use HoloLens as an audio output device to help them more naturally to move in that space. Of course, that's not long-term use, but it's definitely usable. And other things are to use object detection or object recognition when you look at machine parts. So let's say you want to replace a machine, repair a machine, and then you have that little part that you need to replace. Since you have your camera right with you and you're looking at it, you could automatically tie into your backend system and try to identify the part number of the parts that's broken. Yeah. Of course, you could do that also with other things, but in this case, it's just the information is there without needing to use a third-party device to start another application and so on. So most of the scenarios are more integrative and to do things faster and better. The part which I try to say, like learn about things in 3D space, is still a little bit research and development, but I believe we will see a lot more of things, like also in the metaverse context, that we try to learn about a three-dimensional space and annotate the three-dimensional space with information. And their devices like HoloLens can help. I hope that frames it a little bit more.
It does. And then we've got a question from Roland on YouTube, and he asks, what are the typical latency and update rate that you experience with these models?
That's a very good question. So the Onyx model, first of all, when I download this, is around 60, 70 megabytes size. And on HoloLens 2, for this model that has like, I think 8 or 9 different labels, I get around 2 frames per second. So and I use the CPU to do that. I could try to use the GPU to do it a little bit faster, but there are other disadvantages for doing that because it eats into your render budget, which is often the more constrained resource. But I would say for my specific use case, it wasn't so much about tracking things in real time. So it was good enough to take an image like every second and so on and process it in the background. I could even have gone out to the cloud and have it processed in the cloud and then display the result 2 seconds later. That would have been good enough for me. So.
Okay. We've got time for one final question. This comes from Tatiana, and Tatiana would like to know, okay, with the growing rise in popularity of the metaverse, is there still a future for devices like the HoloLens?
I didn't catch the first part. With the growing what of the metaverse?
Popularity of the metaverse.
Yeah, so, I mean, you could simply say HoloLens is a metaverse device, right? So, I mean, so is there a future for a device like HoloLens? I mean, HoloLens is an expensive device, right? And currently there are no other devices really that solve the type of things that HoloLens does, meaning the hands-free computer that can understand the world and you can interact with gestures and so on, while people can still see you. Now, Oculus Quest has some modes where you also get some level of see-through, but it just doesn't do the same thing at this point. So yes, there is something, and there are enough people buying and investing into it. But of course, I mean, there will be more competitors, and maybe in 2 years there will be a completely new device. Maybe Apple will kill the market when they come out with their mixed reality or AR device. We don't know, but we are here to do that journey and look into the future, right?
Great. On behalf of the Global XR Conference, I want to thank you, Andreas Urban, for giving us your time and your insights today. Thank you so much.
James, it was a pleasure, and have fun at the conference.
We will.